What's up, everybody? It's Mr. Prevet. We're here to do some more calculus. Should be a great time. We got 2023 FRQ number 3. This is about some slope fields, some differentials. So a topic that I think should be relatively easy for us. There's a limited number of questions that they can ask about it, but all parts of calculus are difficult in one way or another. So we're going to get better today, hopefully grow in our understanding. But let's get started. Question number 3, it says a bottle of milk is taken out of a refrigerator and placed in a pan of hot water to be warmed. The increasing function m models the temperature of the milk at time t, where m of t is measured in degrees Celsius and t is measured in minutes since the bottle was placed in the pan. M satisfies the differential equation dm dt equals 1/4 times 40 minus m. At t equals 0, the temperature of the milk is 5 degrees Celsius. It can be shown that m of t is less than 40 for all values of t. Okay, so we got this pan of milk. There's a differential that represents the relationship between the temperature and the time. Let's look at part A. So part A says a slope field for the differential equation dm dt equals 1/4 times 40 minus m is shown. Sketch the solution curve through the point 0, 5. Now, obviously, I don't have the solution curve right in front of me, so I'll do my best to kind of model it. We have our m of t over here. We have our t down there. And there's specifically in the slope field kind of these dashed lines that go across at m is equal to 40. And that's going to kind of be a horizontal asymptote of this solution curve. Now we also have this point down here at 0, 5. And all of these little dashes on the solution curve, they represent the slope of our function at that point, right? And if we just follow the dashes, we can create a solution curve. So what it would look like, at the very beginning, my slope kind of looks like this. And then slowly, as we approach m equals 40, kind of starts to look like an asymptote. And we start moving horizontally. So that would be the sketch of my solution curve through the point 0, 5. And this represents, my graph of m of t. So that is part A. Whenever we are asked to graph a solution curve, sketch it, just follow the dotted lines, right? So that's all we got for part A. Not too difficult, not too bad. But we'll move on to part B. Now part B says, use the line tangent to the graph of m at t equals 0 to approximate m of 2, the temperature of the milk at t equals 2 minutes. Now, there are two things that we need for an equation of a tangent line. We need a slope, and we need a point. If we get both of those things, I can very easily find the equation of the tangent line and approximate a point. So, let's look at the point first. The great thing is they give us the point, right? They say it's at t equals 0. At t equals 0, point is 0, 5. So we're halfway there. Now all we need is our slope. And we know that slope is represented by the derivative of a function at a point, which in this case is dm dt. Now at this point, m is equal to 5, t is equal to 0, so I'll plug it into my differential. So it would be 1/4 times 40 minus 5, which is equal to 35 over 4. So that is my slope. Now, does it matter that I didn't plug in my value t into my differential? No, my differential can totally be something that does not involve t. I still get the instantaneous rate of change, or the derivative or the slope of the tangent line at the point. So creating my equation, y minus y1 is equal to my slope, which is 35/4, times x minus 0, or just x, obviously. We could rewrite that. So now it's asking us to approximate m of 2, right? Now m of 2 is going to be represented by when I plug in 2 for x. So I'll get y minus 5 is equal to 35/4 times 2 minus 0. So y is equal to 5 plus 2 times 35/4, which is 35/2. So that gives me my final answer of 45/2. And that is my approximation for the temperature of the milk at T equals 2 minutes. So, like we kind of talked about, we need to find the slope. They give us the point. Once we find the slope, we just plug in a point to get the correct answer. To give it a little bit better in context, you might want to say, 45/2 degrees Celsius. That, I guess, would be a better answer, but I think 45/2 would work fine. But let's move on. Part C. Part C says write an expression for dm or d squared m dt squared. Now this is just kind of the way that we write a second derivative, right? This is equivalent to like m double prime of t. It's just a second derivative, just another way of writing it. Now it says use that to determine whether the approximation from part B is an underestimate or overestimate for the actual value of m of 2. Okay, so let's start by trying to solve for my second derivative. Now we know that our first derivative, dm dt, is 1/4 times 40 minus m. I could also rewrite this if I expanded it as 10 minus m/4. So if I want to find the second derivative, I could just take the derivative of this equation, right? So my derivative of the left side would become the second derivative. And on the right side, the derivative of 10 is just 0. The derivative of negative m/4 would be negative m'/4, or dm dt, right? Now, the great thing is, we know dm dt. It's literally right there. So if I plug this back into m prime, I get that my second derivative is equal to negative 1/4 times 1/4. So negative 1/16 times 40 minus m. And this will be my second derivative as an expression, right? Now, that's great. That's the first part of the question. The second part says use it to determine whether the approximation from part B is an underestimate or overestimate for the actual value. Now, let's talk about estimations in terms of the concavity of a function, because that's what it's based upon. If I have a function that is concave up, like this, and I have a tangent line that I'm using to approximate, well, my approximation is always going to be below our curve. So it will be an under approximation when we are concave up. Vice versa, if I had a function that was concave down, I have my approximation, right? My approximation will always be over the curve. It's an over approximation. So I have this great equation for my second derivative. If I see, okay, my function's concave down, well, then it's an over approximation. If it's concave up, then it's an under approximation. Now, the one piece of information that may not feel super important at first, but it comes up here, is the fact that M is always less than 40. So the temperature of the bottle of milk will always be less than 40 degrees Celsius. Now, if that's the case, then 40 minus M is always equal to some positive value, right? Who knows what it is, but it's positive. When I multiply a negative and a positive number together, I get a negative number. So d squared m dt squared is some negative value, right? And because it is always negative, our function is concave down, and therefore our approximation is an over approximation for the value of m of 2, which we got was 45 over 2. The actual answer is something less than that. Maybe it's, maybe it's 21 degrees Celsius. Maybe it's 20 degrees Celsius. Who knows, right? But this tells us that our approximation was an over approximation. So that is the final answer to part C. This process of taking a derivative of a first derivative to get the second and then plugging back in shows up a lot with implicit derivatives. Sometimes it's not just for differentials. It's like dy dx. They'll ask you to do it. Lots of times that shows up. So it's important to be familiar with it. We'll move on finally to part D. Now part D says use separation of variables to find an expression for m of t, the particular solution to the differential equation that we've had this whole time. I'll write it down again. dm dt is equal to 1/4 times 40 minus m with the initial condition m of 0 is equal to 5. So in order to solve this, it tells us to use separation of variables. What that means is I've got a t over here. I've got some m's there. I need to get them on the same side, right? So I'm going to multiply my dt over to that side. I'm going to divide by 40 minus m on this side. So 1 over 40 minus m dm is equal to 1/4 dt. Now, this is the step that, solves these differential questions, allows us to answer it, and it is a step of integration. If I take the integral of both sides, I'll get rid of the dm and dt, and I will be able to get a solution for this curve. So the right side will obviously be really simple, right? The left side, a little bit more complicated. We have 1 over 40 minus m. I might be tempted to say, oh, this is just the ln of 40 minus m. But our derivative of this inner function is not 1. So we'll need to do some sort of u sub. If I do a u sub of 40 minus m, my du is negative dm. So if I negate the inside and negate the outside of this integral becomes, I'll put it right here, negative integral of 1 over u du, which we know is the ln of the absolute value of u plus c, right? When I plug back in my m, it's the negative ln of the absolute value of 40 minus m plus c. So that is my left side of this equation. My right side, much more simple. The integral of 1/4 with respect to t is just t over 4 plus c. Now these constants are not equal. They're just arbitrary constants. And the great thing is I could actually just only leave one constant on one side because they're just representing a number. We don't know what it is, so I'll just only have it on this side. So now when I plug in my initial condition, I'm going to be able to solve for this constant, c. So I'll plug in 0 for t and 5 for m. And I'll get negative ln of 35 is equal to 0 plus c. So c is equal to negative ln of 35. So now I'll rewrite it again. Negative ln of 40 minus m is equal to t over 4 minus the ln of 35. Now that piece of information that we used in part C is also really helpful here because they tell us m is always less than 40. So this 40 minus m is always positive, right? So those absolute value bars don't actually matter. We can just treat it like normal. Now, we've gotten rid of everything. This is an equation that represents this function, but we're trying to get an expression for m of t, where we isolate m, get it in terms of t. So in order to isolate m, what I would do first is just negate both sides. And now, what I'm going to use to get rid of the ln is do e to those powers, right? Because those powers are equal, e to those powers will also be equal. Now, e to the ln of something, those will actually just cancel out. On the left side, I get 40 minus m. And on the left side, I get e to the negative t over 4 plus the ln of 35. So now in order to isolate m, I could add m over, subtract this over, and I get 40 minus e to the negative t over 4 plus the ln of 35 is equal to m. And that is our final answer for part D. Now you could also slightly simplify this because e to the ln of 35 is 35. So you could, factor that out and also rewrite this as 45 minus 35 times e to the negative t over 4 is equal to m. Both ways are completely acceptable. I think you would get the full points either way. So that is our final answer for part D. A little bit of a mess. Separation of variables is tough. But fortunately, part D was worth 4 points. If we only got up to, solving for C, and this whole separating the variables, doing e to the powers, isolating it, messed you up. If we did everything else, we get 3 points, which is awesome. That's killer. For most of us, the AP exam is not about being perfect. It's about getting a good enough score to pass, right? We want to pass the AP exam. So even if your understanding of isolating m, those algebra skills are a little funky, if you can just integrate both sides and solve for C, you got 3 out of 4, which is on track for a 5. So you're killing it. But that's all we got for today. I hopefully will see you guys soon on another video. Bye, guys.